Hi and welcome to our class CSC352, Introduction to Thread Safety and Synchronization. My name is Rene. In this class, we're going to look at two things. First, we want to look at the problem domain of sharing data across threads and do this in a safe way. And then we're going to move on and look at the most common form of synchronization, that is using monitors. Let's start by looking at the problem in more detail. In the previous classes in C#350 and 351, we learned about asynchronous coding, asynchronous behavior. We also introduced the concept of threads to run work in parallel to our main thread. And now we want to talk about, well, how can we coordinate all of these things that may be going on in parallel in our app? Let's look at this from the opposite side first. So let's assume we have completely thread safe code. What does that mean if code is thread safe? The short answer is it's code that behaves correctly no matter how many threads are executing some code simultaneously. So this means your code should be deterministic, whether you're having a single thread or multiple threads. So what would make cause now not to be thread safe? The main issue is that when we have mutable data that is involved in our data that is being processed, if that mutable data is being accessed by two or more threads at the same time, then there's a danger of corrupting that data. That one thread is reading part of the data that has already been updated, while the second half is still in the old state. And of course, this means we would get incorrect results. And the solution to this problem is to synchronize access to our data by making sure that only one thread can work with the shared object at a time. Kind of like a queue at a bank. Only one person gets to interact with the teller, but multiple people can be filling out their own private forms simultaneously. The problem with synchronizing data is that it often impacts the scalability. The reason is pretty obvious. It forces our threads to work in step with each other and potentially block while waiting for access. So your job as a developer is to provide the correct level of synchronization. It should be just enough to keep the data state pure and valid, but not more than necessary, so we don't impact our scalability and performance. So let's look at why sharing state can cause issues. You will certainly remember from our CSC351 class that threads are executed by a CPU core one at a time. We only get the illusion of multiple things happening simultaneously. The operating system is constantly switching out threads. It's giving each thread a time slice to execute some code. And these thread switches, they can happen at any point in time in our code. There is no way to predict this behavior. And there's also no way to stop this behavior. Of course, a thread can give up processing data, so it just lets the operating system switch to another thread earlier. But other than that, there's nothing we can do. So the thread switches, they happen indeterministically. And these switches are ultimately the cause of our data synchronization issues. For example, let's have a look at a very common piece of code. So this may be from a mobile application, but could also be from a desktop app. Here we have got arrays property changed method. I'm pretty sure all of you have implemented the iNotify property changed interface. So you know there's an event in there which we are supposed to raise in case one of our public properties has been modified. And what you're looking at here is a very common way of implementing a helper method that does exactly that. So we are looking at the property changed event, and we can only invoke it if it's not null. Otherwise, we would get an exception. So we look at the property and we check if it is null or not, and only if it's not null, we invoke it, and all is looking good. But the problem could be that if we have multiple threads that are involved here, that while one thread is checking whether the property is null or not, it may figure out, oh, the property is not null, so it's safe to invoke it. But then another thread is setting it to null. And then the first thread has got a chance to run again, it will try to invoke that event here, and it will fail because meanwhile the property changed event has become null. So we have this danger of change between two threads. If the object is only being read and never changed, then it's generally safe to say that it is thread safe and it's safe to use it across threads. However, if there's even one thread that is potentially changing the object and there are other threads that are using it, then we can run into a problem. There's an important rule in .NET. Thread safety is really only a problem if it's possible for values to change between two threads or more threads, of course, trying to access our data. If the state your thread works with is completely local to the thread or is completely immutable, for example, strings in .NET fall into this category, then you generally do not need to be concerned with thread safety. And it can be a bit tricky to understand when do I have to be concerned and when not. By the way, languages like F#, they have become pretty popular for parallel programming because they greatly reduce the possibility for errors because they force all user-created types to be immutable. And if something is immutable, there's no danger of collisions here. So how can you tell if something is thread safe or not? Well, if you look at the documentation online for all the .NET APIs, then you will always find a section that indicates how thread safe something is. Here we are, for example, looking at the documentation of the random class. And if we read through it, we will find that random is not safe to be used in a multi-threaded environment. And in fact, the random numbers that you could get, they may all be 0, which is of course not as random as they should be. Now let's analyze how we can write thread-safe code. What are our options? Well, the first one is to make our code not use multiple threads at all. Now, of course, that's not always possible. The second thing is we could look at our data that we want to access. We could simply limit the amount of shared data. We could pass in parameters to the threads, make copies of the state, and then return values back out. And if you aren't sharing any writable data, then you greatly reduce the possibility for an error. And third, something that we have already mentioned, immutable objects. If we are using data that is immutable, like strings, that means if you change them, a new copy will be created, then it's completely safe to access these across multiple threads. Each thread will see its own unique pointer to the value, and if something's changing, it's always its own copy. And finally, if you have to share writable state, then you have to consider synchronization mechanisms, and this is what we're going to look at today. Please note that there is no one solution that fits all sizes, and that means you're likely going to have multiple solutions in one project. In another project, you may only have one of them. It totally depends on what you're working on and what exactly your app is about. Let's go through these strategies now. And our first strategy is to limit shared mutable data. If you keep all your data local to the thread, then you avoid the problem entirely. And this approach involves passing all your required data into the thread and saving off the read-only data or making copies of the writable data. And then the thread is going to perform all of its work and calculations, and when it's done, it will return a result back. We can visualize this in a diagram. We start with some known state that we call our master copy, and just for the sake of mobile development reference, we say we are here on a UI thread, and then we create copies of this state. So maybe we get some user input on the UI thread, and now we want multiple threads to work on this user input. So we're going to clone the state as many times as we will have threads, and then we create our tasks that will be associated with threads. In the end, remember our CSC351 class where we talk about the task scheduler. Now every thread/task, and I'm going to use them as synonyms here, They have got their own copy of the state. They are working with these copies. And eventually, they're done processing the states. They will return the local copies back to the main initiator, to the UI thread. And now it's the job of the UI thread, which created the copies, to unify all of the results, to process them. So all this unification is now happening on one thread again. So there's not going to be a problem of corrupt data. Let's now look at another approach. This one is about using immutable objects. Immutability means that you can access the object without really worrying about its state changing, even if that's across threads. If possible, you should always aim to design your shared objects to be immutable. So, like we said before, the string class is one of these examples. All operations that are performed on a string, they will always return a new string object. So if we look at this example here, our class called immutable type, you see if we perform an operation on it, what it's going to do, it creates a new instance and returns that. So there's absolutely no danger that two threads would be able to corrupt the state of this object. Not sharing state or sharing immutable state, that simplifies concurrent programming dramatically. This is really the preferred solution, but sometimes we need to share mutable data. It's simply a fact. So when this happens, we are required to provide synchronization for our shared data. This is by far the most complex approach, and we are going to spend the rest of the time here of this class on various techniques to accomplish this. So let's start by defining when synchronization is actually required. When we started, we figured that synchronization and thread safety may be something that we have to think about if data is being changed. However, this isn't completely accurate. There are some operations that are guaranteed to be completed by the CPU without any interruption. Primarily, these are operations that can be performed in a single CPU instruction, and we call these operations atomic operations. A context switch always occurs on an instruction boundary. And an atomic operation are, well, by definition, thread safe. You can't break an atomic operation into two separate parts. The problem is, however, to recognize atomic operations. That's not always easy. So look at the code that we have here. Simple example, we've got a 64-bit integer, and we've got a set value method, and it assigns something to our int64 value. So the question is now, will this be completed in a single CPU instruction? Yes? No? And the answer is, it depends. So why does it depend? Well, the problem is, in this case, we have got a 64-bit value. On a 64-bit processor, we can hold the entire value in a single register, and we can write the value to a 64-bit memory line in a single instruction. And because it can be done in a single instruction, the statement is by definition atomic. It cannot be interrupted by any other thread once it's started, and the value will always be correct. If, however, we run that code on a 32-bit processor, then it's a bit different, because there the complete 64-bit value cannot be moved and written in a single instruction. So what happens is here that the operation is split into two instructions. And between these two instructions, there's a chance that a thread switch would occur. And now you can imagine what the result would be. Half of the value would have been updated, and if another thread is trying to read that value, it would read part of the old value and part of the new value, which is completely wrong. So whenever we have these non-atomic operations, we must find a way to protect them from being interrupted. But before we get to the techniques, let's have a look at another example. This is also a pretty interesting one. We've got a class called counter here, and we have got an increment method. And all it does is calling counter plus plus. Now imagine having two threads, and both of these threads are calling the increment method. Maybe they're calling it 500 times, maybe 5,000 times, maybe 10,000 times. And the question is, what will the final value of our counter be? And the answer is, well, you can't tell. It's impossible to predict the outcome here. Let's analyze that. It all comes down to atomic statements. Atomic statements are only possible if no interruption can happen. If we look at the counter plus plus operation, however, we will find that this is really just a shortcut for assigning our counter to a temp variable, then adding 1 to that temp variable, and assigning it back to our counter. So this is not atomic at all. In fact, there are 2 chances for a thread switch to happen. And you can really try this out. If you take the code that we just had and you run it in Visual Studio, and you will see that if you run it multiple times, that you will get different resulting values. Make sure to run this as a release build without the debugger being attached. If we have multiple threads that are working on a shared counter, then a thread switch can cause values to be lost. And we want to step through what we just described on the previous slides. We've got our thread number 1 that moves the counter value into a register on the CPU. Thread number 2 is running on a second CPU. It also moves the counter into a register value. Then our first thread, it increments the register. And so does thread 2. Now it's number 1's turn again. It puts the new value back into the shared memory location. Thread 2 does the same thing. And see what the result is. We have lost 1 increment because the 2 threads, they retrieved the same non-atomic value in this case. So the final value that we get is not the one that we really want. For simple incrementations, we have got a built-in class in .NET that is called Interlocked. And Interlocked has got a set of methods that we can use. You can see one example here. Here, for instance, we're using the increment method. And this uses a reference parameter, and it will guarantee that the incrementation here happens atomically. So if we change our example here to use interlocked.increment, the problem is fixed. Again, I invite you to try this out. Go over to Visual Studio maybe and try it. Type that code in and run it again. And you will see that this time the counter has always the expected value. The Interlocked class has got other methods that we can use. You can see them here. There's one that allows us to add an arbitrary value. If you want to subtract something, by the way, you would use negative values. So there's no dot subtract in there. Then we have increment and decrement. That means increase the value by 1 or decrease it by 1. We also have exchange, where we can atomically exchange 2 values. There's also compare exchange in there. So we can do a comparison that must be equal, and then the exchange is going to happen. And all of these operations in there, in this interlock class, they are guaranteed to be atomic. No thread switch will occur until after the operation is complete. So how is this magic achieved? Well, no magic involved. Interlocked is doing this by using a special hardware instruction that affects how memory is handled by the CPU. It ensures that values are always read and written to main memory instead of being cached locally on the CPU. If you use interlocked.increment on an x86 processor, it will result in 2 machine instructions that are being emitted. So keep in mind that based on the processor type, this may change, but the end result will always be the same. So in the case of our increment example here, we will get an LEA, that means load effective address. So essentially this means storing the pointer address into a register. Then we have our inc, INC, this increases the pointer address that is stored in the register. And then we have this instruction prefix called lock. This forces the cache line that is associated with the address to be locked. And what this means is that it ensures that the increment is atomic. No other thread or core can interrupt it or see a stale value at the expense of a little overhead in synchronizing the CPU's cache. So this also answers the question, why would you not always use interlocked.increment? Because it reduces performance. By always writing to the main memory and reading from and preventing the cache to be used, it's of course going to be slower. Let's talk a bit more about caches. You probably know that each CPU has got different caches. If you buy a processor, if you buy a PC, then you get this technical information, says so and so many megabytes of level 1, level 2, and level 3 cache. There are varying sizes and speeds, and these CPU caches are filled from the external memory chips that use a set of cache lines, or blocks as they also refer to. And each cache line represents approximately 64 to 128 bytes of memory. And a cache line is always written either completely or read completely. And the cache lines are shared between all the CPUs that can access the physical memory and are used as a coordination mechanism to access the shared memory resource. And this architecture reduces the processing bottlenecks that are related to the comparatively slow memory chips. It also is used to reduce the contention between CPUs and multi-core systems. So when the CPU cache is flushed back to memory, it must ensure that all other cores do not touch the same memory block, and that all other cores have their local caches updated with new values. And this process is done in hardware by taking a lock on the cache line that is associated with the address that is being updated, what we just saw. If another CPU attempts to access any of the memory associated with the cache line, it will stall until the lock is released. So this lock prefix you just saw essentially forces a cache line lock to occur for the specific instruction being executed. And this makes sure that no other cores can access the memory while it's being changed. And all other cores see the new value. And the new instruction or the instruction being executed is always going to be completed before any context switch can occur. So this is really what makes our increment atomic and thread safe. So this was very, very technical and deep down in the hardware. So let's go back to the .NET and software level again and to C#. We have another example here. And this example is also related to thread safety. And it's one of these examples where people are often very surprised if they experience it first. And there's actually a lot of discussion going on about that. So what do we have here? We've got a very simple while loop here, and we've got a Boolean that indicates whether the while loop should be terminated or not. So as soon as terminate becomes true, the while loop should exit. So let's now imagine that we have one thread that is running the loop, and there's another thread that later changes the value of our terminate Boolean. So the question is, what should happen? I guess by just looking at it, you might say, well, obviously, as soon as the second thread sets our terminate to true, the first one should stop. Because we already learned that threads, they're going to access the shared data of the process, so there's really no problem. But what if the compiler is trying to be smart and it wants to optimize access to this terminate flag here? And believe it or not, this is really what is happening here. What is going on here is that the compiler looks at that code and it sees that, okay, I've got a while loop here and the condition is false. So I will never be able to reach the line where the condition changes, the line where terminate is being set to true. And so the compiler is going to, well, incorrectly optimize this. It says this loop can never end. And it's just going to eliminate it. And as a result, if you run that code, your second thread can set terminate to true as often as it likes to. The loop is never ever going to terminate. And again, I invite you to try this out. You can try this in Visual Studio. The important bit here is that you're running this in a release build without the debugger being attached. Why that? Well, that's making things even worse here, because the optimization, the incorrect optimization, it only happens if you're doing a release build. As long as you're debugging and you're using your debug builds to test, all is good. The second thread will correctly terminate that loop. But if you create a release build, then optimizations will be in place and suddenly it will no longer work. And of course, this can be a nightmare. Imagine you have a piece of code and while you're developing it, all is good, and then you ship it and suddenly it doesn't work anymore. So what can we do about this problem here? Well, to make sure that this particular code here works in all build types, we need to give the compiler and the runtime a little hint that the value can be changed from another thread. There's two static methods that are exposed on the thread class that are helpful here. It's the volatile read and the volatile write. You use the volatile read to read the value, and this tells the CPU to do whatever is necessary to ensure that it is reading the latest value, even if it means dumping the cache line and reloading it. And the second thread uses the volatile write to change the value. This tells the compiler to not perform any code reordering or register caching optimizations here, and to ensure that the value will get flushed to the main memory immediately. You can also use the C# keyword called volatile. By adding this to the definition here of your terminate boolean, it will do exactly the same thing. It's essentially a shortcut. This is simpler to program because it's just placed onto the declaration here of the field. However, it affects every usage of the field, even if you don't need it to be flushed, whereas the deliberate API, that allows you to be more fine-grained. Again, this answers the question, why are we not always using that? Well, because it affects performance. So if you don't have to do it, simply don't do it. Our next step is now to go beyond single statement synchronization. Let's talk about how to protect entire blocks of code. Our goal is now to make multiple statements to be atomic. And to achieve that, we're going to use something that is called a monitor. And we want to learn how to use this monitor. Let's have a look at a more complex example first. Here we've got the very common example of bank transfers. That involves two accounts. We want to remove something from one account and add it to another. And of course, all of this has to be in sync. So if we look at what is going on here, we've got a transfer method. We say we want to transfer a certain amount of money. It's going to be added to our savings balance and it will be removed from our checking balance. And then we've got a property where we can get our total amount, all the money we have. So that's savings plus checking. Looks pretty simple. And as long as we are in a single thread environment, there's absolutely no problem. However, what if we have got multiple threads here? With multiple threads, we can end up in a race condition. Our total amount could be incorrect. What if in the middle of our transfer method, a thread switch occurs? So you see, we have got to fix this. Now let's think if we can fix this using Interlocked. Remember, Interlocked has got add methods, increment methods, decrement. And if we think about it, we'll find that the answer is no. That won't work. We could certainly change our savings balance and separately our checking balance, but not both of them at the same time. So really, Interlocked does not help us. We've got multiple statements here that have to be made atomic. Both of these have to happen in one step as a single operation, because only then is it impossible for a thread switch to occur between these two calculations. And to achieve this, we can use the built-in synchronization feature of .NET that is called a monitor. A monitor is working with reference types as locks. So this helps us to ensure that only one thread accesses a specific protected resource at a time. Most commonly, that resource is some sort of mutable data. It could also be a block of code. What's interesting about the API is that it does not define what the lock object is. Instead, it allows you to use any agreed object as a lock. Let's dive a bit deeper into that. When we use the monitor API, we first have to decide which object we want to use as a lock. Whoever has got the lock, you can also think about this like a token that you're giving to certain persons. Whoever has got the token is, for instance, allowed to speak. All the others have to be quiet. So it doesn't really matter what that token is, as long as everybody follows the rules. The same thing is true here. We just define one object that acts as our lock. And whoever has acquired the lock, they can access our data. So now let's introduce our two threads. Both have agreed to use the same object as their lock. Now, thread number one is trying to access our data, and it finds that the token, the lock, is there. It can take it. So now thread one is able to perform its work. And later, thread two is arriving. And thread two finds that, the lock is not there. I can take the lock. Again, my comparison, the token is not there. I'm not allowed to speak. I have to be quiet. Eventually, thread number one is done. It releases the lock. It returns the token. And now the second thread can grab it. Now the second thread owns the lock. It can perform its work. And later, it should, of course, return the token. So how do we now perform this in C#? What's the code like? Let's start with the lock. This is easy. It can be any object, and in fact, it should be any object. The best practice convention is to use a private object that is scoped to the code that will need to access the data. That ensures that the lock visibility is limited and that other developers that might modify this code in the future won't be tempted to use the same object to protect other things in the application. With the lock object, or the guard as it's called here, in place, we can use the monitor API. And this has got two static methods. The first one is the enter method. We call monitor.enter, passing in our lock to acquire the lock. And here's what's happening. If no other thread currently owns the lock, then it will take it using monitor.enter and execute the code that follows. If the lock has already been taken by another thread, then monitor.enter will wait. It will just sit there until the lock is returned. And we return the lock by using monitor.exit, again passing in that guard object as a reference. We still have a bug forever, even if we add this monitor.enter and monitor.exit into our transfer method of our banking account, because we have only protected the spot where we update our balance information. If you look at our total amount property, you see that this includes summing up the savings balance and the checking balance. We want to add these two, and again, there's a chance that while one thread is trying to do that, another thread is changing things. So the runtime, the .NET runtime, doesn't know the relationship between the lock and the protected data. We are responsible for doing that. So here in this case, we must make sure that we use the very same lock also inside our property. Let's go back to choosing your monitor object once more. We already learned that it should be a private object. That's really the recommendation here. But there are also things that you should totally never do. For example, don't use this as a monitor object. It may be tempting because you can use it as a reference and there's even code out there that does it, but it's a bad idea. It's not private, it's not controlled by you as far as the lifetime is concerned. Some other piece of code might be using the very same object to protect something completely unrelated, and as a result, you may end up synchronizing things against each other that don't have to be synchronized. Worst case, you end up in a deadlock. Also, the object that you are using as a lock, it doesn't have a direct relationship to the data that it is protecting. It's completely up to you to define that relationship. So you can use, if for example, accessing a list or something or collection, you can use the object itself. That is something that you find, but again, it's kind of against the recommendation. Now it's time to do a little exercise. If you look at the lab instructions, you'll find that there's an existing application and we want to add a monitor in there so that we can safely access a shared resource. When you're done with the exercise, I invite you to come back to the video and continue. All right, welcome back. So one thing to watch out for when using the monitor API is to really make sure that you always have correct pairs of enter versus exit. Also, you got to understand that monitors are re-entrant on a single thread. Calling enter multiple times on the same thread will increment a counter. That means you must call exit the same number of times. Notice the bug in the logic that we have here. We're allowing our method to return after calling enter without calling exit. So if another thread attempts to acquire the lock, it will be blocked, and it will be blocked forever. We call this a deadlock. So I want to fix this. We're going to move our check to the start of the method, but this code still has a problem. Let's say we are generating an exception, maybe an overflow exception, because something is going wrong in our calculation of the savings or the checking balance. So what are we going to do then? Well, we still got to make sure that we exit the monitor. So the best practice when working with monitors is to always guard the enter-exit relationship, and good solution here is to use a try catch or a try finally. So that way exit will always be called before leaving the method, no matter how we leave it, whether something goes wrong or we succeed. But guess what? This is generating overhead, right? Monitor enter, try finally, monitor exit, and you put this everywhere. You want to use a lock? Well, there must be a better way, and there is. There's a shortcut. In C#, you find the lock statement. And as a parameter to the lock statement, you use the very same guard object that we just learned about when using the monitor. And if you create a lock statement around some code, then it will be turned into monitor enter, try finally, monitor exit. It's exactly the same thing. One downside of using monitor enter and the lock keyword is that the way to acquire the lock is really indefinite. What if our owner never releases the lock? Or what if something goes wrong and, well, we're sitting there? So maybe you don't want to wait forever. Maybe your code is supposed to try for a little while and then give up. Using the lock statement, you can't achieve that. However, using the monitor APIs, it can be done, because there's monitor.try_enter, where you can specify for how long it should try to acquire the lock. And if it fails, it will simply give up. So now please go back to the exercise that you started previously, where you used the monitor APIs, and try to replace them with the lock statement instead. When you're done, please come back to the video. So, welcome back. In the previous exercise, you added the lock statement, and we also introduced the monitor.enter and monitor.exit APIs. And this allows us to protect our resources. You should always be very aware of what you are protecting and choose the proper granularity for locks versus resources. If you use the same lock to protect too many things, you potentially reduce the scalability of your application, because you start synchronizing threads against different pieces of data. So there's no absolute guidance here. It's really up to you and up to the data and the application that you have. You got to think this through. What data is getting manipulated? How many locks should we need? What needs to be synchronized? A good rule of thumb is, however, to use one unique object for each unique resource that you want to protect, unless the two resources are always modified or read together. In our current lab exercise, the one you did where you added the locks, our solution is really too coarse. The reality is that we don't want to synchronize every aspect, every piece of data. In our case, the data is cats that try to access the food. We don't want to and need to synchronize every cat against every other cat. This is something that you may already have seen, and we're going to address that in the next exercise. Along with the lock granularity, another thing that you should consider when using monitors is the unit of work that you perform while you own a lock. Never forget that when a thread owns a lock, other threads that try to attempt to acquire the lock, they will be blocked. They will have to wait until the lock is released. And the amount of work you do while you own the lock, that directly impacts the amount of contention that you will have against the lock. Here we have another example. We're using a private list as our lock. Remember, we can use any object, and in this case it's convenient to do this, although we would probably prefer to have a separate private object, but it does work here. One thing that we are doing here is retrieving some updates from a remote server. So you can imagine that in there it's doing some REST-based calls, and this can take a bit. So this operation could take pretty long, anything from milliseconds to even minutes if the network connection is slow. Maybe it will never ever complete if the server cannot be reached. And this will definitely impact the responsiveness of our application. A better approach in this case here would be to retrieve the updates first, then take the lock and update our data. In this case, we have a deterministic time that is associated with how long we hold the lock. Our goal is to hold the lock for as little time as possible. You should always try to optimize your code and only hold the lock while actually touching the data. And this brings us back to the exercise. So we already found that having the lock statement there, that solves our problem. We don't have any thread issues anymore, but it was a bit too much. So we can do better by refining the lock and reduce contention. So as always, please go back to the exercise, and when you're done, return to the video. Welcome back. Let's now talk about a problem that can be seen if we are using monitors and actually have more than one object that we are locking or that we are trying to guard. Look at this example here, please. Let's say we've got another bank transfer method here, and we are transferring money from one account to another. So in order to make sure that both accounts are updated correctly and reflect the current state, we lock the first account and then we lock the second account. So what if some other thread owns this lock and is waiting for the first one? And the answer is, well, what if? That's a deadlock. This will never ever finish. So what is going on here? Here's a diagram of what is happening. Assume two threads and two resources with unique locks. Now we have thread number 1, and it will acquire the lock for resource A. Then we've got our second thread, and it acquires the lock for resource B. Next, thread 1 attempts to acquire the lock for resource A, but it's blocked because thread 2 already owns it. And finally, thread 2 does the same for resource A, and it's blocked because the other thread, the first one, owns it. And we've got a deadlock. Neither thread will give up the lock, and neither one can make any other progress. So we need to be very careful with monitor-based locks and having two objects or more that are involved here. If we can avoid it, we should avoid it, but there's also another solution. It is a very classic problem that we have just seen here, and the solution could be to take the locks in a specific order. If you wonder now, how can I make sure that the accounts are locked in a specific order? How should I achieve that? Well, you can use information that is on the account objects. Maybe your accounts have got an identifier. Every bank account has got a number. So this could be your indicator. You could say, I compare the two identifiers, and you always take the lower account ID first. By doing that, you remove the possibility that the second account is already owned by another thread while waiting on the first one. You can really use any ordering criteria. It just has to be consistent. Don't believe it? Well, let's have a look at the diagram again. Let's take the locks in a known order. Resource A followed by resource B. Now, thread number 1 takes the lock for resource A. Thread number 2 goes ahead and also wants to get resource A. Can't do it because the first thread already owns it. So it's waiting. Eventually, our first thread will release it, and now the second one can go on. We have just sorted A before B. And this brings us one last time back to the exercise. Using the lock ordering technique, you will be able to improve the solution, because as it is right now, it has a potential for a deadlock. When you're done with the exercise, please return to the video. Welcome back, and we have almost reached the end of this course. So let's wrap up. You have now all the tools that you need in order to protect resources, make them atomic, so that data does not get corrupted when using multiple threads. And you also should understand that thread safety is really a tough problem. It's not easy. It can always be tricky to see the issues in the first place and then to fix them. If you're interested in even more insights, please check out our CSC353 class. This is where we have a look at even more advanced synchronization techniques. Maybe you will need them in the next project you're working on. Thanks for watching this course, and goodbye.